Excuse me, sir, we can't hear, sir.
Okay, Buddha. I hope you can hear now. Huh? Yeah. So, hope you can manage the question. Okay. Hope you can manage the question. This is from your notes. I got this. So, this says that. What is this? This says it is constant pressure. Okay. Forces. So, this says, let me copy this first. So, it's a question. Right? And this says, see, a frictionless piston cylinder device contains 5 kilograms of steam. So then you understand that. Yeah. And then heat is now transferred. So obviously, a closed system, okay? Now this is for sure a closed system. What is this? This is a closed system. Yeah. And determine the work done by the system during the process. And determine the work done. So here you can see that there is a boundary expansion. Okay, there is a moving system boundary. Moving system boundary or the boundary change or the system expands. Yeah, system boundary expands. It is like this. So you can understand this very well, and actually it's a must for you to understand this. Okay, it's a must for you to understand this. Yeah. So this is very, very important, understanding this. And this 400 kilopascal and 200 grams means it's the initial state. Okay, so the closed system at means this is the initial state or state 1. Initial state or state 1, let's say, or state 1. So what is the final state? It's related to this 250 degrees Celsius. Heat is now transferred to the steam until the temperature reaches. So this is related to final. So this is a hint for the final state. Just a hint, okay? Yeah, hint for the final state. So related to final state. Okay? Related to. I would say that because only the temperature cannot say anything about final state. At least for the gases, you need two properties. If you carefully look into this text, yeah, you need two properties to understand the state of that. Yeah, okay. So considering this, now you can outline the solution. Yeah. Make sure you understand the facts first. Yeah, that is very important. So this is something like a balloon, because receiving heat and the work is done. They're continuously receiving heat, it seems. Until the temperature reaches 250, heat is now transferred to the system. So let's see. Identify the facts. This is the process. Constant pressure. Yeah. Determine the work done. Okay. So this is how you can say this. So applying heat. Okay, applying heat to this. So initially you have initial state. Okay, initial state. Let's see if you draw this. Yeah, no choice but you have to draw something. Yeah, yeah. Let's see, this is the drawing the piston first. Here is the piston. This is the piston. Okay. initial state. Let's say like this. So after the heat being received by the system, of course, slowly you can see that during the heat, receiving piston moves up. Quite interesting. Okay, piston moves up. So you have initial state and a final state. Initial state is 1. Quite easy. You can see 200, the pressure is 400 kilopascal. Kilopascal. 200 degrees Celsius. Okay. Yeah. Degrees Celsius. S1. S2. Of course, based on your assumption, it's the same pressure, temperature 250 degrees Celsius. This is the state 2. Okay, state 1 to state 2. And heat is Q12. Okay, heat is Q12. Q1 to 2. Q1, 2. Okay. Heat is Q1, 2. Q1, 2. I use the same, the question. Heat is Q1, 2. So, you know that with this, there is a change in internal energy. Okay. There is a change in internal energy. Initially, let's say U1. Finally, you have U2. You have 5 kg mass. Okay, 5 kg mass. So, since you have 5 kg, you have a big U is internal energy for 5 kg. And small u2 can be for 1 kg. See? Small u2 is u1 is for 1 kg. Now, okay. So this is quite connected with the balloon example and the last week. The lecture, the last week lecture. So if I look into last week lecture, See the piston cylinder. Oh, it's like a balloon. Okay, but here it's the situation looks constant pressure. So you have this kind of expansions. Okay, you have this kind of expansions, and also you can have this energy balance for the closed system. You want to find work plus energy is the internal energy rise. Okay, work plus energy is the internal energy rise. So it's quite interesting. Okay, work plus energy, and the work done is P times delta V. Okay, pressure times the expansion. Okay, is the work done or work transfer we call it. Okay, work done or work transfer is a better term. Well, work transfer is P delta V, P times the expansion. So we have done until certain levels. Have we done this? You can see. So PV to the power n is constant. So we learned this is a polytropic process. Okay. I believe. පුතා මේ හරිය කිරුවද මේ ස්ලයිඩ්ස් ටික ෆැමිලියද කට්ටියට? ෆැමිලියද මේක? මේ ස්ලයිඩ්ස් අපි ඩෙවලොප් කරපුවාද? පුතා, can someone respond? මතකද මේ ටික කෙරුවා? මතකද? Can someone respond? පුතා කියන්න බලන්න මේ විදිහට ස්ලයිඩ් එකක් දැක්කද ඔය කට්ටිය ප්‍රසන්ටේෂන් එකේ?
Yes, sir.
දැක්කනේ? ඔව්.
Yes, sir.
Very good. මේක එක තැනක පොඩි වචනයක මිස්ටේක් එකක් තිබ්බා. පොඩ්ඩක් ඉන්න මම ඒකත් බලන්න. වචනයක මිස්ටේක් එකක් තිබ්බා somewhere. මේක නෑ නේ. Okay. මේ ස්ලයිඩ් එකත් මතකද පුතාලට? Can you remember this slide? මතකද? දැන් කිරුවේ මෙන්න මේකයි. Let's see. This is of course. You can remember this. PV to the power n is a constant. We call this polytropic process. And for different n and c, you can have different curves. Okay. Right side you can see PV in equals c. This is the piston cylinder. This moves down. Let's see. Example. Some can be this way, going up, also possible. We have learned this. Okay, polytropic process. Constant pressure process we have learned. P equals C, constant. Constant pressure. And in this PV diagram, constant volume process is something like this. The red line is vertical. Horizontal means constant pressure process. Changing both P and V, we generally consider a polytropic process. Okay, we generally consider polytropic process. some signal interruptions. Yeah. So you can see here constant pressure process, constant volume process, and polytropic process. Constant pressure process you have learned, and even you learn the Q equals Cp dt for constant pressure process. And for constant volume process, energy balance, for the first law of thermodynamics, you have learned that is Q equals Cv dt. I hope you can remember those. I hope you can remember those. You've done all very well. Constant volume process here. So you can see, same way, we have done constant pressure process also. This is also just recalling the memory only, theory we have done earlier. So here what we have done finally is to get an overall idea about these processes. There can be constant pressure processes, there can be constant volume processes, and there can be pressure and volume both are changing. Okay, so both are changing. PV to the power n equals constant is the polytropic. That is what we consider for the change in P and V. Both, okay. Yeah. So you can see here polytropic for different N and C. You may have different curves. Yeah. So here we start from state 1. Okay. Constant pressure. See, P equals constant lines from state 1 to state 2. Okay. So intermediate state is state S, this middle blue dot. Okay. So you can see constant pressure process. So here Q is Cp dt. Okay. And this heat is same as the enthalpy change. I believe you can remember this. Okay, that is constant pressure. Again, the work transfer, work done is the pressure times the expansion. Constant volume, see, volume remains the same and your pressure can go high or low, depends on the heat interaction. Yeah. If heat is being received by the system, your pressure will go high. If heat is rejecting by the system, pressure goes low. Somehow you can see this way. So in this closed system, constant volume process, constant pressure process, and PV changing. So these are the 3 types. So we have clearly understand this. Yeah. So this is something like a complete knowledge of the closed system. You came to know this. Yeah. A complete knowledge of the closed system. And further down, you can see for this PV to the power n equals constant. Yeah. So work transfer from 1 to 2, W1 to is dW, P dV here, of course, here the sign is negative, right? Because P dV is from the system. So you can consider this is integral 1 to 2 P dV, and later you can put the negative sign if you need. Yeah. So that's how we came until the last slide. Can you remember? So this is the case. Now, so starting here, we are continuing. Okay, we are continuing this with a new presentation. That's what we are doing here. Okay, so 1 to 2 is like this. So closed system. Okay, initial state given, final state also the same pressure, and for the steam, when you know the pressure and temperatures, you can look into steam tables. Okay, you can look into steam tables to get the values of U1 and U2. Okay, anyway, let me draw the, sorry, not to say draw, let me type the equation. Okay, let me type the equation. Instead of typing, I will take it from a slide we have done previous. That would be easier for me. This from the balloon example. So W1 to 2 plus Q1 to 2 is delta U1 to 2. Okay, I believe you can see this. Confirm it. Yes. You can see W1 to 2 plus Q1 to 2 is delta U W1 to 2. Okay. And is the Q value given? No. Okay. Yeah. But the states of 1 and 2, S1 and S2, we can get. So now, if we write some expressions, okay, so this W1 to 2 is for 5 kg. So W1 to 2 can be written as 5 kg times what? The small w 1 to 2 per kg work done. Okay, per kg work done. That is equal to 5 times the pressure times what? Expansion. Okay, pressure times expansion. Expansion. Here you can see pressure times expansion is okay because this pressure is a constant. Yeah. Yeah. P is a constant, that's why you can write this. Okay. Pressure times expansion for constant pressure process. Yeah. You can write like this for constant pressure process. If not for constant pressure, your writing should be different. Okay, your writing should be different. If not for constant pressure. Okay, Not for constant pressure, as you have learned from previous, I believe so. It is this way, even P dV. So if you follow the sign conventions here, from the system, let's say this is, you have to put the minus value, but I will not put the minus value at this time. So pressure times expansion is P delta V for the varying process, but for constant pressure like this example, this is not a case. So again, yeah, changing pressure and volume means, change in pressure and volume means, you have learned it is like this. If not, you have to look into changing pressure and volume means W12 you have to write in this way. Okay, yeah. This is for varying pressures. For PVN equals C. Okay, that is the situation. So for PVN equals C, it is different. For PVN equals C, no choice but you have to look into this. But our case, P equals C. Okay, our case P equals constant. Our case, P equals a constant. So nothing to do with V. Okay, nothing to do with V. P equals constant. Okay, P equals constant. Yeah. So this is the situation. For constant pressure process, this one. For polytropic, you have to do this way. Okay, P5 is the mass, P is the pressure times expansion. Pressure is given here 400 kilopascal, 5 kg. Okay, so W12 you can find. Even delta U12 also you can find it. Okay, delta U12. Delta U12, if you need to look for it, delta U12 is mass times small u12 S mass times U2, okay, minus U1, okay, U2 minus U1. So, if you are just following, okay, simply the typings, it may not helpful for you, okay. Now, each and every typing or writing here, you should understand the basics, the essentials behind. Okay, essentials behind. So that is very important, essentials behind. So if I rewrite W12 5 times W12 5p expansion. What is expansion? Quite simple. It's the increase of the volume V2 minus V1. Okay, quite yes. Okay, so this case is not PV to the power n, so I take this out. So you have W12, you have delta U12, then from Q12 expression, from Q12 expression, you can write W12 plus Q12 is this. So Q12 is delta U12 minus W12. Okay. From that, Q12 is delta U12 minus W12. So you have delta U12, you have W12. Okay. So this is a constant pressure process. Actually, this is quite simple. If you can remember the basics that this is, anyway, let me write this. 5U2 minus U1 is delta U12 minus W12 is 5 times P V2 minus V1. This is the enthalpy difference finally. Okay, this delta Q is mass times delta H. You can rearrange this. Now this will be in quite nice form. U2 plus, yeah, PV2. You can see when you arrange this, U2 minus U1 and V2 minus V1 minus P times V2 minus V1. Okay. So this is equal to 5 times U2 plus PV2. Okay, PV2 minus U1 plus PV1 minus U1 plus PV1. One. Okay, that is 5 times. Actually, P is same as P2 because constant pressure means at state 2, that is P2, though it is mentioned as P constant. So you can say that, okay, this expression U2 plus P2 V2, you can simplify as H. U1 plus P1 V1 is H1. So H2 minus H1. Okay, enthalpy difference. You can see this very well. For constant pressure process, as I mentioned to you, this is 5 times H2 minus H1. It's so simple now. Okay, 5 times H2 minus H1. H2 minus H1. So 5 times U2 plus P2, V2 minus U1 plus P1, V1. So that's why the U plus PV always coming together in many situations. That's why U plus PV we define as H. Yeah, enthalpy. So this has some physical meaning as well. So I discussed this with you earlier times. So you can understand this better when you look into the previous knowledge sharings. So H2 minus H1. So in your, what to say, in your states 1 and 2, so look for this H2 minus H1. Okay. And this is a constant pressure process. Constant pressure process. Quite interesting. So good. So look into the steam tables. This is, of course, to get an answer is quite easy, but if you analyze this, there can be things like this. Yeah. So if you are analyzing, so this 5 is mass really. Okay, 5 is mass. So even to generalize, you can put instead of 5 the mass of the system. Okay, mass instead of 5. 5 is the mass. M is 5. MH2 minus H1 is Q124 constant pressure process. Okay. Okay, this one. So I put this. Good. Okay. H2 minus H1 for steam. Okay. So you can look into the steam tables. You can look into steam tables. Rogers and Mayhew, I believe you have this. Okay. That's why you have to keep this always, and you go for the pressure is 400 kilopascal, your pressure. Okay. So 400 kilopascal means in bar. Okay. 100 kilopascal is 1 bar. Because bar is later which the units actually you should know by now, because 10 to the power 5 pascal is 1 bar. Okay, let me put that also before looking into this. Yeah, 1 bar. 10 to the power 5, 1, 2, 3, 4, 5 pascals. 100,000 pascal is 1 bar. Okay. P, big P, pascal is a name. Yeah. So 1 bar. So simply we can write, generally we write in this way, not this, but 10 to the power 5 sorry, Pascal. That's how we are writing this. That is 1000 Pascal, or we can write this as 100 times hundreds of 1000 pascals. Okay, hundreds of 1000 pascal, 100 of 1000 pascal. That is 1000 pascal means 1 kilopascal. Is 1 kilopascal. So you can write this as 100 times 1000 pascal is 100 times 1 kilopascal. Okay, 100 times 1 kilopascal. Okay, because 1000 kilopascal, sorry, 1000 pascal is 1 kilopascal. Okay, so our case, you have 4 kilopascals. Okay, 4 kilopascals. 4 kilopascals. Okay, that is 4 of 1 kilopascal. Okay, 1 kilopascal, that is 4 of what? 1000 pascals. Okay, 400 kilopascal. Yeah, our case is 400 kilopascal. I made a mistake. So 400 of 1 kilopascals, 400. Okay, so 400 of 1 kilopascal. So 100 kilopascal, you know that 100 kilopascal is 1 bar. Okay, so that is 1 bar. So you can get this straight away here as 4 times 100 kilopascals. That is 4 times 1 bar. Okay, or 4 bar. I hope you can understand. 400 times 1000. Okay, pascals. That is, you can see 4 times 100,000 pascals. Okay, so 100,000 pascals is 1 bar again. Okay, see, 100,000 pascal is 1 bar. So this is 4 of 1 bar. That is 4 bar. Okay, so 1000 pascal is 1 kilopascal, and 100 of 1000 pascal is 1 bar. Okay, 1 bar. So I believe you know this very well. Yeah. So our case, it is 400 kilopascals. So this working fluid, because there is a work transfer because of this steam, the operating pressure seems to be 1 bar. Okay, seems to be 1 bar. Sorry, 4 bars. 4 bar. So S1 at 4 bar. Okay, 400 kilopascal means 4 bar. Okay, why we put it in bars? So S2 at 400 kilopascal means 4 bar. Okay, 4 bar. Oh, sorry. I've done this very well. I've explained here, but I couldn't put the slide. I'm very sorry. Here I'm putting the slide. 1 bar is 10 to the power 5 pascals. 10 to the power 5 means 100,000 pascal. You can see 5 zeros here. Means 100 of 1000 pascal is 1 bar. 100,000 pascal. 100 of 1000 pascal means 100 of kilopascals. Okay, 100 kilopascals. So that's why. So 100 kilopascal is 1 bar. So our case is 400 kilopascal, it is 4 bar. Okay, so also 400 times 1000 pascal, that is 4 of 100,000 pascals. Again 100,000 is 1 bar, so 4 bars here. Okay, so 100,000 pascal is 1 bar. 10 to the power 5 pascals. Yeah. So this familiarity is important. So now you can look into this Rogers and Mayhew. So 4 bar. Yes, 4 bar is here. Temperature is 200. Okay, in the question. But here you can see in the saturated water and steam it is 143. Okay, temperature. So here, okay, at 4 bar, when steam and water remains together, or at 4 bar, to boil water under 4 bar pressure at 143 degree, the water starts to boil. Okay, water starts to boil. But in the question paper, it is 200, means well over 143. Even, not to say well over, even if the saturation or the boiling temperature is 143.6, even 143.7, it is already in fully gas state, and there is a 0.1 extra, we call it 0.1 degree superheat. Okay, so now you have to look into 4 bar, what, 200 degrees. So you have to look into superheat. This may helpful for you to do the previous steam table related questions. So 4 bar 200. 4 bar is here. 200. See, 50, 100, 150, 200 comes here. This line. So here, this is the, yeah, these are the values. These are the values. So here, you can see the specific volume. Yes, fine. Insert. Yeah, if I take a, let me, at 4 bar. See, small v, small u. Yeah. This is until 4 bar. I think this is 200. Sorry, 250. 0.5953 is for 250. This one, 0.5345 is for 200. So I copy this at 4 bar. Okay. And let me copy like this. Good. At 4 bar, you can see 250 is the rightmost column, 200 is this, and this 143.6 within bracket. This is just the boiling temperature or the saturation temperature. Okay, means liquid and vapor both are there, exist at this temperature. Okay, below this only liquid, above this only gas. That's the beauty of this. At this temperature, the water and the steam together. Good. So now you can see here from this case. Okay, you can see from this case. At 200 degrees Celsius, that's a big rain hit, huh? Your H is So this is H. That is H1 is what? 2862. You know the unit. Kilojoule, you can see here per kilogram. Okay. Then at 250 degrees Celsius, H is H2, that is 2965. Okay, quite interesting. Okay, quite interesting. (2965) kilojoule per kilogram. Kilojoule per kilogram.
So we can't see the presentation.
Sorry, Puta. Sorry. Thank you. You have a good sense, eh? Somehow you have a good sense. Yeah. So this one, the bottom, this line from this extract from the steam tables. Okay. So at 200 degree is the second column from the right. You can refer to the entropy here. Okay. You can, sorry, enthalpy here, Hg value. So H value is here. This Hg is for 143.6, but the H value here, 2862. At 200, 2965, at 250. So you have H1 and H2 values. So then if you go to this previous slide, your Q12 value is equal to mass times H2 minus H1. Mass is 5 kilograms times H2 minus H1. What is H2? 2965. H1 is 2862. So 2965 minus 2862 kilojoule per kilogram. Kilojoule per kilogram. So you can see finally this kilogram cancel out to this per kilogram. Finally you have an answer in kilojoules, whatever the value. Okay, whatever the value. So this example, one way it's important because you are dealing with a real working fluid, what do you call steam. Okay, so here to refer to the steam table, you have to have a knowledge about referring the steam table, and you have realized that this is superheated, and you should know how to read the superheated steam table and extract the data. Here in this case, enthalpy. So that is one piece of knowledge. And the other part of this example is this one helps for you to understand the performing of working fluid as a closed thermodynamic system. So constant mass, there is a work and energy transfers. since the energy transfer, the heat transfer is given, work and heat transfers, heat transfer is given, and you manage to write down the energy balance. And based on the energy balance for the given data, okay, even you can derive the energy balance expression here for constant pressure condition. It's another process, constant pressure condition. So you can simplify the energy balance as mass times the enthalpy difference. Mass is a constant mass here, 5 kg. So enthalpies, you are referring to the steam table. So this is referring the first law, the closed systems, real working fluid, and referring the steam tables. So this is a good question. Okay, understand? Yeah. That's why we are analyzing this. Okay, we are analyzing this. And now I'm going to show you this solution where in your textbook, okay, in your notes, okay, in your notes, I'm going to show you this. Let me change to the notes. This is your note, that's why you should keep your notes printed. You have to read this because the support I'm giving in these presentations, this soon, you see even the same Q12, W12, you can see. So this is the solved example. Let me see. The solved example, what is that? I have to look for that. This is the one. See. See. A frictionless piston cylinder device. Okay. So pistonless means, frictionless means if there is a friction, yeah, still, of course, it's a very good assumption. That is supporting for the with the constant mass of the piston, it support for the constant pressure process. Yeah. So this is the question. So solution is there. You can look into this. So work done. Yeah. Is P mass times pressure V2 minus V1. That's all. W12. Okay. W12. Yeah. This is quite simple. Mass times pressure. Because pressure is there. So we evaluated with the energy balance. There, of course, somehow we came for a formulation. So that is a bit long way and a curvy way. But here, mass times, pressure times, V2 minus V1. Okay, so it is like this. Work done. See, mass phi times pressure times expansion. Yeah, there you can get the work done. Okay, there you can get the work done. Work is 5 times pressure times expansion. Yeah. Okay. That's how. So what is this? Yeah. Here we have calculated actually the heat. Yeah. Heat. Yeah. I think we missed the question. Yeah. We managed to find the heat and work done also. It is very simple. 5 times pressure times, see, V2 minus V1, work done. So here you can calculate the work done also, work done. If you need to look into work done, so I duplicate this. So you have to do the work done. Work done is 5 times pressure. 5 is the mass. V2 minus V1 at 4 bar. Okay, at 200 degrees C and 4 bar. Okay, 4 bar. So even previous case and 4 bar. 4 bar is very important. So 4 bar is there. Okay, at 4 bar. So at 4 bar. Previous case, and this is also the same. So at 4 bar. At 200 degrees C. Now V2 minus V1. So we will look into V, volume, V1. Now V is V1. Here you can see V1 is, that is Vg, or the V value here, meter cube per kilogram, 0.5345. So this is 0.5345. Fine. Meter cube per kilogram. Okay, meter cube per kilogram. At 250 degrees Celsius, this specific volume, okay, V is the specific volume. Finally, because per kg, that is 0.5953. 0.5953 meter cube per kg. Okay, so these are the findings. So that's why in this answer, see, 5953 and 5345. Okay, 0.5953, 0.5345. You can see the same in here, 0.5345, 0.5953. So later we can substitute this. So when you substitute, W12 is mass times small w12, that is 5, pressure. Now your volume is in meter cube per kilogram, so you have these SI units. So 400 kilopascal means you turn this into 400 times kilopascal is 10 to the power 3 pascals. Pascals. V2 minus V1. So V2 is 0.5943 minus V1 is 0.5345. Okay. So you can see this is all in SI units, kilograms, pascals, okay, and meter cube per kilogram specific volume. So this work done is in joule. Okay, joule. So if you look into this, not yes, this one. So later you convert it, you can have kilojoules. Okay. The minus sign is because when it comes to the sign convention, okay, sign convention is always work transfer is towards the system, but here expansion is work transfer from the system. So that's why this is minus W12. Okay, and that's why. So 5 times this is minus W12. Okay, so 5 times okay, minus W12. So minus W12 is P V2 minus V1. Because this is work transfer from the system to towards the surrounding. So that's why the expansion is there. So this is minus W1. Okay. So W12 becomes so this is minus. So W12 is you multiply this by minus sign also okay. Is minus P times V2 minus V1. This is therefore, okay, therefore W12 is minus 5 times PV2 minus V1. That's why you see in this solution minus here. Okay, minus 5 means mass, PV2 minus V1. So you should have some clear understanding on that. Okay, good. So that is the question. So polytropic processes. So you can see here polytropic. So we have learned this in a very simple way. Now if you look into your notes, you can see what polytropic, and you can simply connect your most experiential knowledge with this text, so you can understand this very well. Cn equals gamma. We call isentropic process. Isentropic case, the both reversible and adiabatic here mentioned this perfectly insulated, then the process will be adiabatic. The adiabatic process. So I think that is no heat transfer, no heat interaction with the surrounding. We call it adiabatic. And even in this, so you consider some reversibility as well anyway. Isentropics, yeah. So when n equals gamma, we have discussed this. So some practical examples. Air compressors, n is 1.3. Stationary air. So fan cooled air, n is 1.2. Yes. So these are not gamma value, n value. Water cooled air, PV to the power n equals constant. Your n is this. Okay. So this is the work done also. There may be work transfer. This is the work transfer for this kind of polytropic process. Yeah, polytropic process. Okay, work transfer. You can prove this, even I have mentioned that how to prove it. So let me take this with my notes and the presentations. Yeah, I think I will send you the presentation. And this, yes, this previous one. That day we came up to this level. PVN equals C. So I will add a new slide for this. Let me put this work transfer. Work transfer. So related to this, okay? Related to this work transfer. So as further. Picture. It's the case, okay? So your work transfer expression is here. So you try to understand this, to try to understand and prove this. Okay, so this is a complete knowledge for you. Okay, this is a complete knowledge for you. And with this one, constant pressure we have learned, and even constant pressure in the text. You can see some more examples maybe. Let's look into the text. So this is the work transfer. And heat transfer also here. Using the equations, Q12 plus W12 is delta U. So let me put this as well for the completion of the knot. Only the expression I will put. Edit. Heat transfer. here. This is the heat transfer. This is the heat transfer expression. Yes. So work transfer is here. Expression, heat transfer expression is here. So the connection between these two is through the energy balance equation. Okay, through the energy balance equation. So if you need the energy balance equation, let me put this as well. This is the connection. Okay. Delta U12, you can see right side of the heat transfer U2 minus U1. Okay. So Q12 plus W12, you can see minus P2 V2 minus P1 V1 by 1 minus. So this is for PV to the power n equals constant or a polytropic process. So you have a quite, how to say, quite complete knowledge about this closed system. We have started from the balloon example. So we know how to connect the work and heat transfers and the internal energies, and even for the constant pressure process. And this first law of thermodynamics or energy balance, this equation, simplified to Q equals the enthalpy increase, dH or delta H, and that is equal to Cp delta T. Can you remember? Constant volume, Q equals Cv delta T. Two processes. I believe you have this familiarity now. Even see constant pressure process, heat transfer, work transfers. Yeah, let's see. Constant volume process, non-flow. See heat transfer, this one. You can see see. Transfer here, you can see Cv delta T. See, Cv delta T is here. This is in your note. You have enough familiarity to understand this. So you have a very good note really. So read this. And constant pressure processes. Heat transfer you can see here. Yeah. So I put this also into slide. You have enough capacity now to understand this. Okay. And it is important to read the notes. Okay, equally important. It's very important to join the class, and equally important reading the notes, because as I mentioned to you, my lectures are always supportive for the notes, and I'm not doing the notes because you should look into the notes. That is very important, because nowadays we should promote the self-learning. So, but we are really supporting you with a very good background preparation for this. So we are doing our part. You have to do your part as well. Yeah. This is a solid example. We just did this. Yeah. So nice. Even I will put this here for your understanding. This is the one. So after discussion, but this one makes you complete, but the note makes complete. So you have to read, understand everything, and you are really have this note. So you have this, even I can transfer the slides to you. So you have a very good guide to receive this knowledge. Yeah. Okay. See, all we have discussed. Polytropic process. This is about polytropic process. So let me put this part as well, because we have done this. Okay, we have done this. We have done this. So polytropic process. Since we have done, we can put this into note. Imagine if I'm doing the notes, I will start from here, I will put the note here and then I will discuss. You cannot learn thermodynamics in this way. So I came with a very natural approach to give you upfront familiarity about this. It was very nicely done. And now you can look into this. Okay, you can look into this. And these notes are with you already. Okay, these notes are with you already. So notes are with you already. Work done also you have done. And there is a solid example. You can try this. Okay. When you try this, you feel that, okay, you feel that how complete your knowledge becomes. Okay, another one. You can try this by yourself. You can refer the formula. You can refer the formula for work done, because work done formula, you can refer it. That's all right. Yeah, that's all right. Even you can try to do the integrations. Yeah, that is not a big deal. That is not a big deal. But remember, maths is not technology, but it is important to know some outcomes of integrations at least. This is about a petrol engine cylinder. Initially, before expansion, it is 30 bar and 800. The gas expands through a volume. So initial and final, you have the ratio 8.5 to 1, because you need only the ratio maybe. And occupy this much after expansion. So this is V2. When the engine is air-cooled, the polytropic expansion is 1.15. What is the temperature and pressure of the gas after expansion? And what is the work output? Okay. So you can do this. Okay, I'm not going to do this. You can do this. So you have to get some support from the formulas. So what is the temperature and pressure of the gas after expansion? This is nothing. So PV to the power n equals constant. So that is the expression. So you can look into this polytropic. Okay, polytropic. So PV to the power n is constant. Okay, polytropic, very nice. So PV to the power n is constant. Throughout the expansion. Okay, so this is the polytropic process for polytropic process. PV to the power n is constant. Yeah. So then you can write this. You know state 1, let's say P1, okay, P1, and V1 to the power n, okay, is equal to the final P2 V2 to the power n, okay. Temperature and pressure of the gas after expansion. So here you can derive from this what is P2 and what is P2 value. P2 is P1 times V2 V2 by V1, okay. Let me try to type this. V2 by V1. So V2 by V1. to the power n. I think I have to retype it. Yeah, this is the best I can write. Okay, V2 by V1 to the power n, and V2 by V1 is 8.125. Okay, so this is P2, huh? P2. This is P2. So you can substitute here. P1 is 30 bar. Okay, so you can use in kilopascals maybe. Or 30 bar, even bar is okay. So same units, so 30. V2 by V1. What is V2 by V1? It's 8.5 to 1. So V2 by V1 is 8.5. To the power n. What is n is 1.15, which is quite, so this should be the answer in bar. Okay, this is the answer in bar. So V2 by V1. Yes. So you can look for the answer. Okay, you can look for the answer. I take this out. So somehow you can see the pressure. After expansion, it is P2. So you have to draw the sketches and all. And the temperature as well. Okay, temperature as well. So you have to evaluate the temperature as well. Okay, you have to evaluate the temperature as well for the temperatures. Okay, so you have to look into some more expressions. Okay, you have to look into some more expressions. Right? Yeah. So So here you have to take this expression, okay? Later we will come to gas laws. Later we will learn about the gas laws. To evaluate the temperature, you have to use this expression. That is that. P1 V1 by T1, assuming the perfect gas. Okay. Assuming the gas is perfect gas. It's here. You have to use this expression. Okay. This is from the perfect gas expression. So you can use this one to derive your T2 value. Okay. So you can go through the example and you can see from how to get this. Okay, you can see how to get this. There is a perfect gas equation, pressure times volume as MRT mass, specific gas constant, and T. PV equals MRT, M in kilograms, R there is a unit, M times R times T. So P in Pascal, V in meter cube, M in kilogram. So PV is kilojoule, so that your R becomes joule per kg per Kelvin, because T in Kelvin. Okay, T in Kelvin. So remember this. So, and PV can be in joule, PV. So PV together, let's see, PV in joule or kilojoule. Okay, either in joule or in kilojoule, both okay. So let me make this a little bit bigger in size. P in Pascal or kilopascal. Okay, P in Pascal or kilopascal. V in meter cube, M in, yeah, beta, P in the slide. Yeah, you can see it. Yeah. M in kilogram, V in meter cube, P in Pascal or kilopascal, because kilopascal is, I think for industrial law, that is better. T in Kelvin. So therefore, PV, therefore, PV in, because pressure times volume, if P is in Pascal, PV is in joules. If P is in kilopascal, then if P is in kilopascal, PV is in kilojoule. Okay, in kilojoule. That's how it is. Then R is in joule per kg per Kelvin, or kilojoule per kilogram per Kelvin. And this is a constant, and it's a constant. R we call specific gas constant. Later, for the gas laws, I'm going to do this one. This is R. Okay, specific gas. Not to say a specific, this is how to say perfect gas. Perfect gas constant R. This for perfect gas. Okay, perfect gas constant. Yeah, at the moment, yeah, just remember this as perfect gas constant. That is okay. Yeah. So this perfect gas constant, we can use this, it has the specific gas constant as well. So the name of this, so perfect gas constant, yeah, that is okay. Or we call it specific gas also. Don't worry, this one I'm going to share with you afterward. R, okay. These are the units. So anyway, at this moment, for only this case, you can use this. P1 V1 by T1 equals P2 V2 by T2. The reason is, from this expression, PV equals MRT. Okay, PV equals MRT. For this MR can be PV by T. Okay, from this, MR is PV by T. So MR at 1 and MR at 2 equals constant. No change, unchanged. Unchanged. So for a constant mass, okay, so no change of the air mass. So PV by T at state 1 is same as PV by T at state 2. Okay, so PV by T at state 1 is PV by T1, PV by T2. I put this as the subscript. Okay, so you can see it. It's the same. PV by T1 is PV by 2. So you can see one, you can write it as P1 V1 by T1. Okay, instead of PV by T2, that is P2 V2 by T2. So anyway, this is not the, actually this is not the way I should share. I will be sharing in a better way, but for this moment, just to solve this example, you consider this. Okay. So your volume, so they are asking the, sorry, temperature. So T2, so T2 is quite easier now. T2 becomes, yeah, T2 becomes, yeah, from this, you can derive T2. How? T2 becomes P2V2 divided by this P1V1 by T1. This is quite easier now because you have calculated the, from the earlier equations, you have calculated P2 value, then V2 by V1, you know, you have the P1 value. So anyway, let me rewrite this. This is equal to P2 by P1, okay, P2 by P1 P2 by P1 times V2 by V1, okay, V2 by V1. I made a mistake here. V2 by V1, okay. No, this is okay, eh? This is okay. And okay, this is times T1. Okay, finally, this T will come like this, times T1. So this is your T2 value. So P2 by P1, V2 by V1 times T1. So see, P2 by P1 is V2 by V1 times to the power 1.25. Okay, that is T2 equals P2 by P1 is this. This is your T2. V2 by V1, there is a value given 8.5 by 1. So that is 8.5. T1 is 800 Kelvin or degree Celsius given. 800 degrees Celsius. So here T1 is 800. You have to convert this to Kelvin. So let's say 273 plus 800. something like this. So this is in Kelvin. Okay. So that's all, Putala, for today. Give me a second. I had to plug the power supply to the computer. Give me a second. Yeah. Yeah, back again, Putala. So you can see this. So you can see this. That's how you can get the answers for this. Actually, this is not about getting answers, but to understand the systems and the behaviors of pressure and volume, the connections and all. How to interact with the surrounding as heat transfers and work transfers. So this is just for a matter of understanding this. Okay. කොහොම හරි ගාන හදනවා කියන එක නෙවෙයි කතන්දරේ. එහෙම එකක් නෑ. ඉස්සරලා එහෙමනේ. කොහොම හරි කියලා. Somehow here no such thing. Somehow you have to understand this to the fullest. Yeah, that is your priority, to understand this case. Yeah. Again, it's a piston cylinder, no matter it's a petrol engine. So this is the case. This is a polytropic process. Polytropic process for this question. It's a polytropic process. Yeah. You have learned this. So it's the same. No much difference. So now you can feel that you have to do something. Yes. Other than listening. Okay, Bhutana? Yeah. So you have to understand. So that is very important. අවශ්‍ය මූලික දේවල් ඔක්කොම ටික බහුතරයක් දීලා තියෙනවා. So you do this one. So I think that's all. And